All right, welcome to this explainer. We are strapping in today for a super high-speed, honestly slightly chaotic whiteboard journey straight into the world of quantum physics. We're talking the fundamental fabric of reality, billions of dollars, and a tiny, tiny blip that literally changed science forever. So get ready, because we are breaking down the God particle. Okay, let's dive into this. To actually understand why this is such a massive deal, we gotta start with one of the biggest cosmic mysteries out there. How did particles get mass in the first place? Think about the absolute smallest building blocks of the universe. Why isn't everything just floating around like weightless ghosts?
Section 1. A universe without RAS. So in a totally massless universe, what happens? Well, it is just pure, tiny space chaos. Without any mass to slow them down, particles would literally just zip around endlessly at the speed of light. They'd never be able to clump together. And, no clumping means no atoms, no stars, no planets, absolutely no TikTok, and tragically, no pizza. Everything is just this blindingly fast soup of particles.
Moving on to Section 2, the invisible Higgs Field. Now, since planets obviously exist, right, nature clearly needed a way to slow those wild particles down. So, back in 1964, a group of scientists proposed what's called the Brodt-Englert-Higgs mechanism. They realized, hey, what if the entire universe is filled with this giant, invisible energy field? The idea was that particles don't actually have mass on their own. Instead, they get their mass by interacting with this hidden field. And this brilliantly illustrates the concept. Think of this invisible field like a super thick layer of cosmic mud. Take a photon, which is a particle of light. It's basically wearing quantum rain boots. It zips right through the mud, completely untouched, still going at light speed, so it has zero mass. But then you have a heavier particle, like a quark, and it just gets totally bogged down. That struggle, the effort it takes to push through the field, that is exactly what we measure as mass. Which brings us to Section 3, the goddamn particle. So in physics, every quantum field has a corresponding particle. And for the Higgs field, that's the Higgs boson. But you've probably heard it called the God particle. Want to know why? It's hilarious. In 1993, Nobel laureate Leon Letterman actually wanted to title his book The Goddamn Particle because it was just so incredibly, frustratingly hard to find. But publishers being publishers, they chopped it down to the God particle. And physicists everywhere have basically been cringing ever since.
All right, Section 4, smashing protons at CERN.
To actually prove this invisible cosmic mud field was real, scientists had to catch a Higgs boson in the act. And this sparked an agonizing, decades-long chase. I mean, we're talking all the way from theoretical math on a dusty chalkboard in 1964 straight through to July 4th, 2012, when CERN finally, triumphantly announced to the world that they found it. And let me tell you, this was not a cheap side project. It took roughly 4 decades of research and a staggering $14 billion budget to pull us off. They had to build the Large Hadron Collider, literally the absolute largest, most complex machine ever built by human hands, just buried deep underground in Europe. So the crucial point is, you can't just catch a Higgs boson in a jar, you have to violently force it into existence. Step 1, you accelerate protons to basically the speed of light. Step 2, you smash them head-on into each other. Particle go boom. This massive collision causes a ripple in the Higgs field. And finally, step 3, you desperately try to detect that ripple, which is the Higgs boson, before it instantly decays into tiny, microscopic debris. It is literally the ultimate needle in a haystack situation. Seriously, only about 1 in a billion collisions actually produces a Higgs boson. Over the years, scientists at CERN have analyzed a mind-boggling 10,000 trillion proton collisions. Think about that number. And they've produced millions of Higgs bosons just to map out these extremely rare, high-energy interactions with unprecedented precision. Let's move to Section 5, Beyond the Standard Model, and see how this builds into the future. Now, what's really interesting here is realizing that finding the Higgs definitely wasn't the end of the story. In fact, everything we just talked about, you, me, the stars, the planets, the Higgs itself, all of that normal matter makes up a measly 4.9% of the entire universe. Just 4.9%. The rest of it? It's a complete, total mystery made up of dark matter and dark energy. So physicists are really hoping the Higgs boson acts almost like a portal to help us figure out what that dark matter actually is. They're testing some incredibly wild, almost sci-fi level theories, like supersymmetry. It's this idea that every known particle has a heavier, hidden sparticle partner. They're basically hunting for these heavy ghost particles that might literally be the glue holding our galaxies together.
So, tying all our chaotic Stickman doodles together today, science. It's wild, it's expensive, and it's absolutely beautiful. We actually found the invisible web that gives the universe its weight, but we are nowhere near done. The universe has hidden rules, and we are still actively discovering them every single day.
Which leaves us with a totally mind-bending thought to wrap up our explainer today. If the Higgs field is what gives mass to particles, what exactly gives the Higgs boson its own mass? And really, what other invisible fields are just sitting out there, waiting in the dark? Think about that for a bit. Keep exploring, stay curious, and I'll catch you in the next explainer.